Hey everyone, thanks for joining FSI 307. My name is John Fermento. I'm a senior solution architect here at AWS. I'm lucky and fortunate enough here to be presenting with a colleague of mine from the Vanguard Group, Ayub Hazarati. Today we're here presenting on their personalization at scale with Amazon SageMaker, talking about a really unique use case called the personalized glide path. So really quick intro, we're going to dive into what PGP is, talk about what a glide path is, and then we'll talk about building this solution. So covering data generation, model training, surface analysis, and surface building and analysis, and then some really awesome conclusions, and then we'll save some time for Q&A. So really quickly, just to level set for those of you who aren't familiar with the Vanguard Group. The Vanguard Group is one of the largest investment firms in the world, and as of July 31st, 2001, have just under $8.1 trillion in global assets under management. The firm is located or headquartered in Valley Forge, Pennsylvania, and offers just over 400 different funds to its over 30 million investors worldwide. And early on, Vanguard knew that digital advice would be a large initiative and really a great opportunity for growth for the firm. And they've set an audacious goal by 2025 to have 1 million advice clients. And to reach this goal, Vanguard created a line of business dedicated to digital advice called Enterprise Advice to tackle this challenge. And that is the group from which Ayub is part of. Enterprise Advice, or EA, as you may hear through our presentation today, was born in 2017 and is really a cloud-native arm within Vanguard and one of the largest consumers of AWS within the firm. EA focuses on a variety of things, but the one really neat thing today we're going to talk about is the personalized glide path. So today you're going to learn how Vanguard used Amazon SageMaker and specifically SageMaker processing to generate millions of data points to create this hyper-personalized experience, and then how they used Amazon SageMaker for model training and inference. So just to level set, we're talking about glide path and personalization, but what exactly is a glide path? So if you're like me and you purchase a 401k and you're typically purchasing a target date fund, you may see like target date 2060 as an example. And what that is referring to is basically, that fund will mature and be ready for consumption in 2060, and it's using a glide path to determine asset allocation. So in a nutshell, a glide path is basically determining the asset allocation of a fund to its target date. And you can see here in this image that as you're earlier or farther away from that target date, the asset allocation mix is going to typically be more riskier assets, more high return assets such as equities. And as you get closer to the maturity or the target date, it typically shifts to more stable assets, if you will, maybe bonds or something that has less fluctuation in value to ensure that you have the value and funds when you need it for retirement. And so to create a more personalized glide path engine, a lot of data is required. And this is like hundreds of millions of pieces of data, which we'll touch on in a minute. And I'll show you how Vanguard used SageMaker to accomplish this. But with that said, this idea of a personalized glide path existed within Vanguard for many years. And it was really cost prohibitive. A lot of compute resources are required to generate this massive amount of data. And this could potentially cost the firm millions of dollars. And Ayub will touch on this later in the presentation in a really neat section where he talks about some of the cost-benefit analysis they did when looking at various options for building PGP. But the cool thing is this problem was solved by the Enterprise Advice Group within Vanguard using Amazon SageMaker. And they were able to solve it by using the elasticity of AWS. So being able to spin up 120, 130 really large instances to get the compute necessary to generate the data required, all using Amazon SageMaker and SageMaker processing. So to create this personalized glide path experience, Enterprise Advice is leveraging the Vanguard Lifecycle Investing model. And you'll hear us refer to this as the VLCM. And really what this is it's a goals-based glide path construction model, and it was developed by the investment strategy group within Vanguard. And really what this does at its core is it's assessing trade-offs between the expected lifetime spending that can be funded from a portfolio and taking into account uncertainty about that spending due to market risks. And this model takes into account market trends, geopolitical trends, really all kinds of market variables, and is refreshed regularly. So Vanguard created a lifecycle utility calculator for asset allocation. And really what this is, it's a Python-based tool based on the VLCM concepts I just talked about. And really what this is, it's a glide path utility. And you'll hear us refer to this as the certainty equivalence, or C, throughout this presentation. And it's really just a utility function. And this tool is doing the main utility calculation before calling the VLCM for glide path recommendations. And just really quickly about how this works is there's 27 kind of static inputs, if you will. And these static inputs are domain knowledge or industry best practices that have been accumulated by Vanguard over their years in business. And then there are 8 profile-specific inputs. And these on the slide are covered under the 8 combinatorial inputs. And these are like risk aversion, loss aversion, savings rate, spending ratio, retirement age, current salary, and portfolio value. And as you can imagine, these 8 really vary from investor to investor. So as an individual, I would basically, put in some of these metrics of how I feel, right? So if I'm more risk averse, I would put that in. And what's really neat is this model takes into account all those things, but also takes into account a lot of other variables such as capital market trends, inflation rates, etc., and then spits out, or on the other end of the output, is a glide path CE. So with PGP, it develops 1,198 potential glide paths that an investor could be on. So it gets really personalized to the very specific scenario. And that's where PGP leverages the Vanguard lifecycle model we just talked about. And EA has built PGP to provide this highly personalized experience to investors when compared to a standard glide path that may just take into a couple accounts and may only have a handful of different glide paths to put you on, whereas PGP expanded this to 1,198 different glide paths. And again, these are very specific to the persona or profile of that particular investor situation and changes over time. And so how this works is the team in EA built surfaces like you can see here on the slide for more than 9,000 personas, taking into account savings rate, spending ratio, age, all those inputs I just talked about on the previous slide. And when an investor is leveraging PGP, everyone's assigned a base glide path. And then as your inputs change, maybe you want to change your retirement age or you want to kick up your savings rate, PGP will then calculate the max C. And you can think of that as the potential max return or another glide path that aligns with these new inputs. And then what's going to happen is it's going to take the difference between the max C and your base glide path. And if PGP determines that there are at least 3 basis point improvement with taking that max C, you're going to be moved to that new glide path. And the goal here is to really ensure that the investors are getting the maximum return possible given their inputs from the VLCM model. And as you can imagine, accuracy is extremely important when it comes to making financial recommendations. And EA and AU took a lot of effort into determining what model accuracy made the most sense. And they were able to get within 3 basis points or a 98.5% accuracy level for the max CE. And for the base profiles, it's determined to be 100% accurate. So now, really quickly, I want to talk about the overall architecture. The bottom of this architecture diagram covers the creation of the base profiles. So Ayoub and the team in Enterprise Advice needed to get more than 110 million base profiles and feed those into Amazon SageMaker processing. And they're leveraging, as you can see here, the AIML VLCM Python tool and basically bringing their own container. They're generating the base glide paths for all those personas, putting it in an S3 bucket, and then using SageMaker Studio and basically marrying the CEs to the profile information and moving those to S3, which I'll talk about in a second how that's used. At the top end of this diagram is the data generation for the ML model. And this is that max C, or you can think about it, the 1,197 other glide paths that each persona or profile could use. Here they're using a lot less data. They're using 10 million random profiles. And Abe will go into more detail about why they landed on that number. But in short, they're able to basically create a model, train the model, and run inference using a smaller subset of data to get within that 3 basis points of accuracy I talked about. So in this scenario, they're taking those profiles and again using the AIML VLCM model and using 130 very large Amazon SageMaker processing instances, in this case the M5 24XL instances. moving that into S3, and this time in 10K chunks are marrying the profile information to the max CEs created and putting that in S3. The difference here is now they're taking that data and training a model and running inference on that model to create the remaining glide paths. And at the bottom right corner in data aggregation and surface analysis, they're basically combining those two data sets and then putting in an S3 bucket for other systems within Vanguard to leverage PGP. So now I'm going to hand it over to Ayub, who's a senior data scientist with the Vanguard Group, to really dive into how this is all possible.
Hello, I'm Ayub Hazrati. I'm a senior data scientist working at Vanguard Enterprise Advice. And thank you, John, for introducing me and the project. Here right now, I'm going to deep dive into the different steps of the project and with the fair amount of details that how we use SageMaker processing and Amazon AWS cloud computing extensively to handle our PGP project. The first step in our architecture is that we identify what type of data we are going to generate to train model on top of that for the basically max CE data generation. For that purpose, we first generate the exhaustive the data point that we need for each profile. Let's say profile I, J is just need each of them 10, 15,000 data point, but we cannot generate all of them. We random sample 5 to 6%, 8% from each profile, and then put them together and create a data set that will be ready for the data generation. This is basically, it seems a small step toward this project, but it is essential things to do random sampling. Once we have that input list generated, the goal is to generate 10 million data points with large instance of SageMaker processing. We picked the 24 X large instances. The reason behind selecting 24 X large instances is that they have a large amount of compute capacity, 96 CPUs, and each of them has 386 gig of memory, which in our case, since the AI ML VLCM is producing a lot of intermediate data, we need large amount of memory as well. For the MaxCE model training data, we generated up to 10 million with 120 instances of 24 X large instances. If you do the computation, you will see that we utilized more than 11,000 CPUs and 46,000 gig of memory. And this process, this compute happened for 3 weeks. So then the question is that how we can make sure that the workload of all those 120 instances is uniform and each instance is getting a similar type of workload. By that, I mean that some of the profile need a lot of computation, some of the profile needs less computation. For example, if somebody's age is 25, is going to retire at 70, in comparison with somebody that is 64 and is going to retire at 65, the amount of computation that is needed for this two profile is different. But if we cluster the same profile into some instances, then the workload among the instances is not uniform. So how we have to make sure that the instances workload is uniform, we basically shuffle the input list. And then we decided that we can basically divide that 10 million into the chunk of 25,000. And once an instance start data generation, that data generation go run for producing 25,000 data points. But the point is that reading that input list is usually takes 10 minutes, 15 minutes, and then usually the instances cannot wait for one instance cannot wait 10, 15 minutes to the other instance finish the reading job. So we created an auxiliary fault, a helper fault that is just basically track the available range of indexes. It's a list that contains around 60 numbered integer number that when an instance arrives, it knows that basically which chunk of 25,000 is available for reading. The way that it happens is it's basically synchronizing among the SageMaker instances that each instance, when each instance start coming to data generation, it first wait around 60 seconds. So basically, it's just a buffer time that we selected to just be not the big time, not a small time, just some 60 seconds. Then it just read that helper list and check, pick up the available index and available the chunk of data that is available for the data generation, and then update that helper file in the S3, and then the next instance is know that the, for example, chunk number 1 is not available anymore, and it start the data generation from chunk number 2, and then that instance read the main data that it takes around more than 15 minutes, and then select basically the 25,000 indexes and run the data generation. So in this way, it makes sure that basically instances, they don't replicate, they generate replicated data. They don't, their workload is basically evenly distributed among them, and they work nicely with each other. The next step is that when an instance has 25,000 data points, it has 96 CPUs, so it has to basically do the data generation among CPUs. So we divide 25,000 into 96, a list of 90 to 96 of same size, and each CPU is responsible for data generation. For this case, we just use a multi-processing package of Python that's available in the Python SageMaker and SageMaker in AWS SageMaker processing. And then we just use the process function, and just it's just automatically synchronize among the CPUs the data generation. The main function for that is the work function that actually is calling the main AI ML VLCM for that specific input. For example, one specific index is just called the AI ML VLCM to run input and just do the data generation, provide a naming for the data for that generated data, and store that in the S3. The whole process of creating a SageMaker processing, because of the tools and basically the document that AWS provided for us, is pretty straightforward. We just need to change a few arguments in the code to make that SageMaker processing happen. For example, here we just change the number of instances to 120, what type of instances we are going to use, and then how long this basically SageMaker processes is going to run, and what is the entry point in the Docker file. So we just use the code that has been provided for us through AWS and push that Docker image into the ECR, and it's just run for the desired time to do data generation. The next step after data generation is that, okay, we generated data, and right now we have to aggregate data. But the problem is that the way that our AI ML VLCM is generating data is just generate a glide path for one basically profile. So we will end it up with 10 million, more than 10 million SAP file or the pickle file that they are stored in different basically folder in S3. And the total size of the generated data, 10 million data point, is more than 500 gig of data. So if we want to just use the regular for loop, just iterate through this folder and just put this data together, it takes forever. It takes at least a month for the gathering, for the aggregation of this data. The way that we handle this, we again, since we had the compute power of 24x large instance, we just make that data aggregation in parallel processing format and utilizing the power of 24x large instance. The way that it's worked, pretty straightforward. We have a file reader that is actually reading one SAP file, and then we are using the pull function that basically is synchronizing among the different CPUs, and it maps the file reader to a specific bunch of SAP file that we are going to read. So basically, with this two simple function and using pull function, we can utilize the 96 CPUs of 24x large instance, and just it is 96 times faster than just using one basically CPUs. The next step is that, okay, we have those 1198 Galite Pass CE, we aggregate them, but we have to merge them with the profile information, that 27 features, that some of them are combinatorial and some of them are not. So the way that it works is just we use basically a SageMaker Studio to aggregate these two datasets and just read these two datasets. Since each dataset has each data point has an index file, index number, we just merge them through index and aggregate these datasets with each other. But the problem is not data aggregation. Once we did data aggregation, still we cannot train model on top of aggregated data. We have to store data on CSV so that all the models can access to the CSV files and just train model on those CSV files. So the way that, because also storing those data into CSV file it takes time. We take the same approach. We just say that, okay, we divide the big file into the chunk of 10,000 and then save them in S3 as CSV. But the process of saving files in S3 as CSV, we just did it in parallel processing with the same technique using the pull function and a file writer that the pull function mapped the file writer to the selected CSV file. So basically we first aggregate data through the DF maker, and then we divide that. It is a DF data frame of 100K, length of 100K. We divide that into the 10 data frame of 110K, and then use the pull function to write that in the S3. So the way that it works during the training job, it takes around 3 minutes to read all those 1,000 CSV file of basically 10,000 with 24x large. If we just don't do that in this way, the reading of the file with one basically CPUs, it's not even possible. We try that, we just fail. But in this way, it is working very nicely, and we can read all those 1,015 CSV files in 3 minutes with 24x large instances. Okay, right now we have the data ready for model training. So we have to start training model with the SageMaker processing and compute power that we have. We basically experimented with different options that we have. We first consider this problem as a single output regression model if we consider Galite Pass as a feature. The second way that we can treat this problem is multiple output regression model. So basically we have input feature and then the output is 1198 Galite Pass basically CEs. And ranking model. Ranking model, it works in the way that basically we rank the Galite Pass and then filter top 30 or top 50 Galite Pass with the highest CE, and then we just generate the CE value for top 30 or top 50 with AI ML VLCM. For each of these approaches for the model training, we applied a set of techniques in each of them. For example, for single output regression, we did some dimensionality reduction and complicated feature engineering. For multiple output regression model, we experimented with different neural network architecture and distance metric learning of k-nearest neighbor with KD3 algorithm for finding the nearest neighbors. At the end, when we trained so many different models with the compute power that we had, these are the results. We trained deep neural network basically that has 1198 Galite Pass. These are actually the leading models. The deep neural network that has 1198 Galite Pass CE is just multiple output neural network. We trained this type of model on with the P3 instances of SageMaker. We reached to the accuracy of 9 basis point or 95.3. The RNN type of model that has one that is predicting the CE. So basically, in this case, we are using Galite Pass sequence as a feature. The RNN structure here is basically the Y shape, the Y structure of the sequence model. We also trained this type of RNN model on P3 instances, and it's just reached to the accuracy of 80 basis point or 90%. For the XGBoost model, we again predict the CE, but here we just only use the first three principal components of glide path as a feature. And for the training XGBoost model, we reformat the dataset in the shape that we can use the training facility that AWS has, and just we use that Docker for the training. It reached to the accuracy of 93% or 10 basis points. While we was experimenting with so many different models, we noticed that the KNN model, just the training with all the weight, all the feature has same weight, has the basically better performance. So we try to learn the distance metric and just instead of simple KNN, learn weighted KNN, which it needs we need to learn a distance metric for that. We experimented with an approach that is known cross entropy method. This cross entropy method is a method that can be parallelized, and it is a good point because we can basically utilize some big SageMaker instances for the model training, and we use 5, 6, 24x large instances to learn the distance metric for the weighted KNN. And it worked out, and it just reached the desired accuracy that we were looking for. During this phase of data generation and model training, we noticed the correlation between the data size and the model accuracy. The model accuracy increasing rapidly up to a point that up to the 2 to 3 million data point. Basically, when we are on 2 million data point, the accuracy of MAC-C is 3 basis points. And after that, it's still the accuracy increase, but it needs more data to increase the accuracy. For example, it's just to reach the accuracy of 1.5 basis point, we need 10 million data point. And if you just compare the data generation time, you can see that it's just the difference between 2 million and 10 million is less than 7 days, and for 10 million is 21 days. So basically, it's a huge impact. It is a huge difference between basically the 3 basis point and 1.5 basis point. So if we just narrow down to the available option, so basically what was other option that we can tackle this problem? Okay, so what we are looking in this problem is CFE, which is basically max CE minus baseline CE. Each profile has a max CE and has a baseline CE. So we have 4 options that we can basically produce this CFE. First, we can train a model. So basically that single model produce both max CE and baseline CE for us, and we just happy with one model. The point of that one model is that because the overall accuracy for CFE that we needed is 3 basis points, the accuracy of the single model should be 1.5 basis point, which means that it's possible that we have 1.5 basis point mistake in the max and 1.5 in baseline, so the accuracy of the model should be 3 basis point. The second option is that, okay, we basically produce 2 different models, one for the max CE and one for the base CE, but the overall accuracy should be 3 basis point. Option 3 that we just go through that and discuss the architecture is actually option 3. We are generating the baseline glide path with AI ML VLCM. Why we are doing that? Because it's just only one glide path and it is fast. And then the max CE with with the model training. And option 4 is a ranking model. We rank the top, we rank the glide path and find the top 30 or top 50 glide paths and put the baseline glide path with that top glide path and generate all of them basically with AI ML VLCM. If we compare those 4 options in terms of the data required, the cost of the data generation, the training cost, and basically the time that is needed for the basically data generation and mostly training, we can see that why we specifically go for option 3. Option 1 is basically it needs 10 million data point. The cost of data generation is around 350, and but since it is only one model and it just needs less training cost. the time that is required for data generation is around 3 weeks. Option 2 needs 2 models. We need more data generation for the basically glide path and less data generation for the max CE. The overall cost of data generation is less, but the training cost is little more because we have to train 2 models. And the overall data generation cost is around 2 weeks because the baseline glide path generation is basically fast. Then for the option 3, we are generating all the baseline glide paths with the AI ML VLCM and the max CE with basically the model. In this case, the cost of data generation is basically a little higher than option 2, but it is close. On the other hand, we have only one single model in this case, and the model is trained on a smaller data set, so basically the cost of training is lower, and the overall the time that is needed for data generation is lower. So if and option 4, we did quite some research with option 4, and it couldn't basically beat option 3, so we stopped searching about option 4 and we move forward basically with option 3. Another question that came, and we did some research about that, is that what if we just generate a small amount of data and keep experimenting all machine learning model with that small amount of data, we might reach to the desired accuracy. That's a good hypothesis, but the point is that if we just generate a small data, it needs a lot of time of data scientists and a lot of time of research, and basically we have to experiment with so many model training, and still it's not yet guaranteed that we can reach to the desired accuracy. So basically it is a risky decision. On the other hand, large amount of data is just need one model, and basically the model is pretty simple. So basically we don't need a lot of time of data scientist or the data modeler, but it just need more compute power, and it is guaranteed that we will reach to the desired accuracy. Here the technology cost is scary in comparison with option 1, that the human cost was scary. Right now, the option 3 of the previous slide that I discussed, that it lies somewhere in between option 1 and option 3. Okay, when we basically train all this weighted KNN model with KD3 distance, with basically KD3 as an approximation algorithm for finding neighbors, we need basically to use that model for inference. We found that the neighbors of, for example, we found that the neighbors of some points that, for example, the age is between 25 to 30, the neighbors are between 25 and 35. We don't need to search all through up 70. So if it was the case, then we just partition data, we edit data into 9 set of a smaller data set, and then train 9 basically weighted KNN model for each data set, and then use that for the model inference. So then each model is responsible for the inference of a specific age range. So we need another we need another SageMaker processing to handle that, but this SageMaker processing, we just only need 9 instances because we have 9 model, and then basically the rest of synchronizing among instances for the model inference is similar to the data generation. We have a helper list that contains 1 to 9, and then whenever an instance starts working, it knows that it's responsible for which model and which data to do inference. So with this technique and editing data and training 9 a smaller model on the data set, the inference time was shortened a lot, and the whole inference took around 4 hours, and the inference cost was less than 200. It means that we generated 100 million data point, more than 100 million data point, basically with 3 basis point accuracy with $200, only $200, and in 4 hours with this basically ecosystem. Then we have max basically CE. We have to generate the baseline CE and merge them to build the CFE. For the max, for the baseline CE, the procedure is simple. We just has the profile, and we just pass through that those profile through the SageMaker processing, and because it just need to generate one Glide Path C, it is pretty fast, and we were able to generate those baseline profiles in a day. The final step of this process before doing surface analysis is to merge the max C and baseline C. So we have two sets of the data set, one for max, one for baseline, and we have to merge that. It's pretty straightforward. We just use SageMaker Studio, even not the large instance of the SageMaker Studio, because we store the data profile wise. So basically each profile was 10, 12,000 data points, and we just read the max and baseline and merge them and store them in the S3. And the final step after having all those CFE surfaces, we have to do visualization and breaking point analysis. That it's another discussion, but the result of that breaking point analysis, we generated this surface, and whenever it is in the green area, it means that if that person is changing, saving, or spending, still the baseline glide path is the best glide path. But whenever it just go to the color to the red area in the corner, it means that there is a better glide path for this person, and we can switch basically the base glide path to that glide path for this specific persona. Okay. In conclusion, so this personalized glide path is one of the basically goal of advice, and basically we are going to provide individual personalized glide paths for advice clients right now. Personalized glide paths relies heavily on computation. So basically we have to consider various market condition, investor risk, loss aversion, and so many financial and demographic situation of an investor. So this problem looks scary. It wasn't possible without having access to a lot of computing resource. But AWS computing resource enable us to just change the status of this project from unsolvable to solvable. So in the worst case, if we just don't use any machine learning or training, we just can pay 5-6 million and just generate this data set with AWS cloud computing. But the problem right now is solvable if we just use the computing resources. But using the basically the machine learning alongside with the AWS cloud computing and SageMaker processing, not only caused that the status of the project changed from unsolvable to solvable, but decrease the cost of the project and the cost and time of the project significantly. It's just from millions, 5-6 millions, we just can finish this project right now with 200-300K. And keep in mind that we have to refresh this project every 2 years. It's not a one-time project, and it's just have to be refreshed every 2 years. And in long run, it's just save a lot of basically money, and we can do it in a short amount of time. Thank you for paying attention and basically listening to Personalized Glide Path project at Vanguard.